Okay, guys, so here it is, lesson 4 out of energy and momentum. So we're looking at a concept today called energy conservation. The idea behind energy conservation is that depending on the size, depending on the scope of the system that you're looking at, i.e., how big or how small your focus is, what we understand to be energy conservation is going to change. So, what we've looked at this point is we've said that work is going to change the energy of a system. Now, if we narrow our focus to something like your hand throwing a ball, it goes up, it comes back down. If we look at if this is the scope of our system, energy at the beginning is 0. It's not moving. There is no potential energy here if we call this level 0. But then we've brought in some work from the outside. The ball does some work, it flies up, lands back down, and again, at the end, the energy is 0. So if we look at the system here, we're jumping straight into the example here. If we look at what's happened here, kinetic energy at the beginning is 0. Potential energy at the beginning is 0. Kinetic energy at the end is 0. Potential energy at the end is 0. It's not moving and it's level. We can see that the throw has done work. We've increased the energy of our system by doing work. As this thing rises and falls, well, what's happening to the potential energy here? We did 30 joules of work. We added 30 joules of energy to our system, which means that as the ball rises and then comes back down, it's got to use or only has access to those 30 joules of energy. So if as it's rising a little bit at every step of the way, even coming back down to here, we know that the potential energy plus the kinetic energy, or maybe this isn't obvious, but the kinetic energy plus the potential energy has to be equal to the work put in. At the beginning, there was no work. And there was no energy. We put 30 joules of energy in, so at every step of the way, the energy that's available to the system is those 30 joules. So at this stage, if the potential energy is 1 joule here, then the kinetic energy has to be 29 joules. They only have these 30 joules of energy to work with. And then every step of the way, as this thing rises, if it has 15 joules of potential energy here, it's going to have 15 joules of kinetic energy. If at the top, well, it's an interesting question. At the top, what's it going to have? Well, at the top, we know that the reason it is the top is because for a brief moment, this thing stops moving. So the kinetic energy here is 0, so then what's the potential energy? How much energy is potentially available to this ball? Well, if it has no kinetic energy, all the work that we put in is what's available to this thing as far as its potential goes. So it's got 30 joules of potential energy. And then as this thing comes back down, once it's level to with where it started, we know that the potential energy here has to be 0 because the height is 0. Potential energy is mgh. So then how much kinetic energy does the ball have at this point? Well, it has to have 30 joules. Well, and then there was the catch. So at this point, work has been, at the beginning, work was put into the system. As we catch it, work has to come out. There has to be negative work done to bring us back to 0. Well, how much work has to be done? Well, this has to be the negative 30 joules. 30 joules was put in, so 30 joules has to come out here. So, where does it go? Well, if you've ever caught a ball barehanded, especially if it's been moving relatively quickly, there's two things to consider here. Well, one is the fact that your hand is going to heat up. The friction between your hand and the ball is where some of that energy is going to go. And you're going to hear it. You hear the slapping sound of your hand catching a ball. And that's part of where the energy is going as well. So if we look at our system here, was energy conserved? Well, not really. If we consider the ball's energy, we threw it, so it increased. As it rose and fell, the total energy was constant. It changed from kinetic to potential, but the total energy was constant. It was equal to the amount of work that we put in. And then as we caught this thing, the energy decreased. So, actually, I should have made that green. It decreased. So then, well, what do we say? Is energy conserved in the system if the system is the ball? Well, no, not really. But what if we step back and say, so if this is my system, was energy conserved? Well, no. But what happened? What about the universal energy? The energy of the universe. Did anything change there? So if we now look at this bigger system and consider the universe. Did energy come from outside the universe to make this thing happen? Well, obviously, I think the answer there, we should understand that the answer is no. The work was always, as far as the universe was concerned, that energy existed somewhere else in some other form. The cereal you had for breakfast this morning gave you the energy to throw the ball. It rose, it fell, you caught it, it turned into heat and sound. In the scope of the ball, energy was not conserved. But in the scope of the universe, as we zoom this thing out further, of course energy was conserved. The idea here is that universally energy is just conserved. It's just changed form. So universal energy is constant. It's just changing forms. That's an N. Sorry. Changing forms. So flip the page here. Let's keep going. So when we use the conservation of energy theorem, what we're looking at is this idea that as the system energy changes, we get work being put into our smaller system by this non-conservative force, whatever it is. So this non-conservative work is the change in the system energy due to some applied force. Maybe we added energy to the system, or to friction, we pulled energy out of the system. And this non-conservative force is zero if gravity is the only... because gravity, we deal with gravity. Say gravity is dealt with via potential energy and kinetic energy. But the other piece to this is, the other way we can interpret this conservation of energy equation is that the energy of the universe itself is constant. The work being done in this non-conservative force, in the zoomed in system, comes from somewhere. It comes from chemical energy from outside the system. Or heat energy, pulling energy out of the system. That heat doesn't leave the universe, it just exists in some other form. So, on a narrow scope, energy cannot be conserved, while on the grander scope, energy can be conserved. In fact, we know it is. The energy that exists here in our universe is all of the energy that's available to it. And so that lets us, even just these simple ideas, we have to talk them through so that we can use them appropriately. So let's look at this. We've got a pendulum here with no air friction. The system energy is constant. We've got a pendulum in a vacuum. So if at the beginning here there is no velocity, it's being held here at this point, and we're told that it is 10 joules of potential energy. If it's not moving, it also has 0 joules of kinetic energy. 0 joules. If there is no friction, there is no there is no non-conservative work. There is no work being done. There's nothing dragging energy out of the system. So if there's no energy being pulled out of the system, that means at any given point along the way, the total energy of the system must remain the same. So at the beginning, if we added these guys together, energy total equals 10. So at each step of the way, my total energy must also equal 10. So if here the potential energy is 8 joules, then as this thing has started to drop, it's beginning to pick up speed, therefore it is beginning to acquire kinetic energy. Well, how much? If it's got 8 joules of potential here, that means 2 joules must have been converted to kinetic. At the bottom here, there is no potential energy. We're calling this level here, in this particular question, we're calling this height h equals 0. If there's no potential energy at the bottom, that means all of it must have turned into kinetic energy. Again, there's no friction, work is 0. At this level, as the pendulum is starting to rise again, it's gaining potential energy and slowing down to this top spot. The kinetic energy here has to be 1. Again, every step of the way, it has to add to the total. Because the system energy is constant, there's no friction. The only difference between example 2 and example 3 is that in example 3 here, we've got a pendulum with friction. So we're told here that there is 10 joules of potential energy. It's not moving, so at this stage, there's 0 joules of kinetic energy. But now we've got to look kind of at the entire system before we can piece this thing together at each step of the way. If we look at this stage here, the total energy of the system at the bottom, where it has no potential energy, is 6 joules. 0 potential, 6 kinetic means the total energy here is 6. The total energy was 10, it's now 6, so how much work was done? We've got friction pulling energy out of the system. So that must mean, to go from 10 to 6, 4 joules of energy has to have been pulled out. Then we're told as this thing starts to rise again, the friction of the air pulls out more energy. 2 joules in fact. So if we had 6 joules here, we lost 2. That must mean the total energy at this point is 4 joules, which means energy total at this point has to equal 4 joules because there was 6, 2 was pulled out, which means the kinetic energy here is going to have to be 2 as well. Universally, energy was conserved. System, the energy was not conserved because friction's pulling energy out of the pendulum. Flip the page. Same idea, except instead of a pendulum, we're going to look at a ball rolling down the hill. One thing to note here that's important is energy is path independent. Energy does not care how you get from point A to point B. So here we are at point A, here we are at point B. The idea that this is sloped ultimately doesn't matter when we're dealing with potential energies. If we were talking about, if we were going to do this as a kinematics problem, well, that could be fundamentally different, because it's not a nice straight fall. But as far as energy is concerned, it doesn't matter. That's going to be an important piece of information. So let's take a look at it. We're going to find the unknowns. We're told that this is a ball rolling down a frictionless track. Frictionless is important. Frictionless means no outside work. If there's no outside work, that means 0 and 0 for my non-conservative workforces, which is, we like this. Makes our life a little bit easier. At the top, we're also told that this thing starts from rest. So if it starts from rest, there is no kinetic energy here. At the end, there is no potential energy. The ball is at the bottom. So what's the kinetic energy going to have to be if no work was done? If it's, by friction, for example. In this case, the kinetic energy, because there's no work being done here, total energy remains constant. So if I had 25 and 0, I'm going to have 0 and I'm going to have 25. And then right in the middle, halfway down, half of my energy is going to have changed. So I'm going to have 12.5 joules of potential energy and 12.5 joules of kinetic energy. Because the total system energy has to remain 25 joules. And I'm halfway down. Let's look at this guy here. If I've got, let's take a look at the technical comment here first, I guess. As far as the ramp is concerned, the normal force isn't doing work. So again, remember, work we had was work equals force times distance, and force times displacement, and force and displacement, as long as they were parallel to each other, the work was being done. In this case, the normal force is perpendicular to the ramp, so it's perpendicular to the displacement every step of the way. So there's no work being done by that particular force. Let's look at example 5 here. If I've got an object being raised, and in this case we're told the mass is being pulled up at a constant speed, we want to know what the energy is here. Constant speed implies that the kinetic energy is constant. Well, if kinetic energy is constant, at every step of the way it has 800 joules of kinetic energy. It has some V not equal to 0, and it has some V not equal to 0. And let's see, it's V initial not equal to 0, V final not equal to 0, and we know that V initial equals V final because we're told it's constant velocity, so my kinetic energy at the beginning and the end must be the same. At the beginning, this thing's at the bottom, height is 0 above this surface, so there is no potential energy. So we can see here, at the bottom, my energy total is 800 joules. At the end, my total energy is 2,000 joules. So that must mean work was done to bring in energy from outside our system to increase the height of the block. Well, how much work was done? We started with 800, now we're at 2,000, so the work done has to be 1,200 joules. We're going to look at three more examples here. Do I want to do both of these? Yeah, I'll do both of these. So, and these will be relatively quick. So, if I've got potential energy and kinetic energy of the ball each step of the way, I want to find all of my unknowns. So I've got 2 I don't know here. I don't know my work in either place. I don't know my kinetic energy, and I don't know my velocity. But we do know that as far as this system is concerned, there is no air resistance. If there's no air resistance and the ball is just falling, we do know this, that work is equal to 0. We're told that the mass of the ball is 20 kilograms and that it starts at a height of 300 meters and it starts at rest. Starting at rest tells us if V equals 0, that must mean my kinetic energy equals 0 as well. So KE equals 0. My potential energy is given to us by mgh. We know the mass of the ball, we know gravity, we know the height that it starts at. So this is going to be 20 times 9.8 times 30 meters gives us a potential energy of 5,880 joules. And because, well, no, that's it. Potential energy and kinetic energy. That's my potential. There's my kinetic, which means E total at this point is 5,880. No air resistance means no work done at any stage, which means my energy total has to remain the same, joules, all the way down. So we can use the height at each stage to find out what my potential energy is, and then kinetic energy is relatively easy to find. As potential energy decreases, kinetic energy increases. So at this stage, my potential energy, again, is given by mgh. We have the mass of the ball hasn't changed, it's 20 kilos. Gravity hasn't changed, but the height has been reduced to 14 meters above my h equals 0. So my potential energy here is 2,744, which means my kinetic energy has to be what? Well, my total minus my potential is going to give us the kinetic here, 3,136. Well, which means how fast is my ball going at this point? Well, that's relatively easy to find out. Well, we know, because we know kinetic energy is given to us by 1/2 mv squared. So it's going to be 1/2 times 20 v squared equals 3,136. Let's look at this piece here. I know that, so I've got 10 v squared equals 3,136, so v squared is going to equal 313.6, so v is going to equal 17.7 meters per second. Square root both sides there. So my velocity here, it started at 0, and now we are at 17.7 meters per second. The ball is picking up speed as it's falling. Potential energy is being turned into kinetic energy. I mean, the same calculations can be done here. I'll leave these for you to try. But I will tell you what they are. The potential energy at 6 meters, you should find it to be 1,176. The kinetic energy you should find to be 4,704. Which means the velocity that you're looking for should be 21.69 meters per second. Give that a shot. Example 7 is very similar. I'm going to slide this up here, except now we're dealing with air resistance. Lots of these things, though, some of these ideas are very similar. We're told that a 20 kilogram mass is in free fall starting from rest with air resistance. With air resistance is going to give us these two terms here. So, and then at rest, is going to tell us my kinetic energy is 0. So we're starting with 1,200 joules of energy total, because there's no kinetic and it's all potential. We lose 300. Okay, so my E total here was 1,200. At this stage here, if we've lost 300 joules of energy due to the air resistance, my total energy available to the system at this point is the 1,200 minus the 300, so that's 900 joules of total energy available to the system. If at this stage, 800 joules of it is potential energy, that means 100 of those joules of total energy is kinetic. Which means if we compare our two examples, at this stage, no, I can't compare the two examples perfectly. Never mind, we won't do that. We'll hold off finding the velocity here for a sec. You can find that relatively easily. Ke equals half mv squared. I won't hold off. I'll just do it now. E equals 1/2 times 10 times, or 20 rather, times v squared, which means 10 equals v squared, so v equals whatever root 10 is. 3.16. second. Down here at the bottom, we're told that the potential energy is 250, the kinetic energy is 250, so the total energy at the bottom here is 500 joules. So if we had 1200, we lost 300 to give us 900, and we've lost some unknown amount to give us 500 joules of total energy. Well, what work has been done by air resistance? Well, the work that's been done by air resistance is all the missing energy. So we've got negative 400 joules of work done here, and we'll leave that velocity off. It's easy, relatively easy to find. But the idea here, what I'm trying to show you with these two examples, is the impact that air resistance or a non-conservative work is going to have on how we treat each one of these questions. Let's do one more example here. Make it a little bit more interesting. We've got A and B here. We'll do it relatively quickly. We've got a frictionless ramp in part A. And in part B, the speed at the bottom of the ramp is something. Find the energy lost to friction. So the difference between A and B is A is frictionless, B is friction. So I'm going to treat these separately side by side. So we've got A over here, we've got B over here. So let's do A first. If the ramp is frictionless, write a work energy equation and find the speed of the 1,000 kilogram roller coaster at the bottom of the ramp. So this is my setup. Here I am initially, here I am finally. So we're going to use energy to solve this particular problem. So we're going to use our work energy equation. So energy initial plus work equals energy final. We're told the ramp is frictionless, so in part A, my work is equal to 0. At the beginning, it has some speed, it has some height, so I'm going to have potential energy at the beginning, I'm going to have kinetic energy at the beginning, and that's going to be equal to the things at the bottom, so it just has kinetic energy at the bottom. So potential energy is mgh initial plus 1/2 mv initial squared equals 1/2 mv final squared. One thing to notice here is because we have a mass in every term, if I divide this whole side by m and this whole side by m, my m's are going to cancel there and there. If you are lost here with how I divided out these fractions, or the m out of both of these, effectively there's two separate fractions here, please review your algebra or fire me an email. I can help you with that. What we've got, I canceled my m's from both sides. Is gh initial plus 1/2 v initial squared. That's going to equal 1/2 v final squared. It doesn't actually matter what the mass of the roller coaster is. Now I can fill this all in. 9.8 times 10 plus 1/2 times 2 squared equals 1/2 v final squared. The algebra here is easy. 98. 2 squared is 4 divided by 2 is 2. I multiply that whole thing by 2 and I square root. I'm going to get a v final is 14.14 meters per second, assuming that the ramp is frictionless. Let's assume it's not. We're told here that if the speed in part B, if the speed at the bottom of the ramp is 12 meters per second, write a work energy equation and find the energy lost to friction. It's going to start the same way, except here in part B, the energy is lost to friction. That's going to give me that work term. It's non-zero now. So I've got potential energy at the beginning, I've got kinetic energy at the beginning, I have work being done here, and now I've got just kinetic energy at the bottom. Let's fill this thing in. mgh initial plus 1/2 mv final squared, mv initial squared plus whatever work is done by friction is going to equal 1/2 mv final squared. I do not have a mass in every term now. I don't have a mass there, so I cannot cancel it, so now I've got to include it in my calculation. So I've got a 1,000 kilogram roller coaster times gravity times its initial height above the ground plus 1/2 times the mass of my roller coaster times its initial velocity squared plus the work term is going to equal 1/2 its mass times its final velocity squared. I'll just show you what this thing looks like. So 1,000 times 9.8 times 10. So this is 98,000 plus 0.5. Sorry, 0.5 times 1,000 times 4 is 2,000 plus my work is going to equal 0.5 times 1,000 times 12 squared equals 72,000 joules. So, well, what's going on here? I've got 100,000 joules plus my work equals 72,000 joules of energy at the end, which means friction has pulled energy out of the system. Well, how much? Subtract that over, and we're going to get that the work done by friction to pull energy out of the system is negative 28,000 joules of energy. Same question. In part A, no friction. In part B, friction. We can see how things have changed there. It's going a little bit slower. 14.14 meters per second versus the 12 meters per second. That's a lot of heat been pulled out. So I'm going to give you some questions. Give these things a shot. Do what you can. I want you guys to take a look at questions 1, 3, 4. I want you to do A and C. Take a look at 8. Take a look at 9.